A vector space is a mathematical structure. It is an abstraction of many concrete mathematical structures that satisfy a common set of properties. Here, we're going to look at two mathematical structures. On the surface, they look very different, but in fact, they share a lot of properties in common. So the first thing that we're going to look at is a set of solutions to Ax equal to 0, where A is an m by n matrix with entries from some field F. As usual, this 0 here denotes the m tuple of all zeros. The second structure that we're going to look at is given by the set of quadratics in X with coefficients from F. And we are going to call this set over here n of A. So n of A is a set of X in Fn such that Ax is 0, and the set P2 denotes this set of quadratics. The first property that we're going to look at is the following. If you take any two elements from n of A and any two elements from P2, you'll see that if you add them, the result is also in the set. And the way to see this over here is, if you look at A times x plus y, that's the same as A times x plus A times y, and that's 0 plus 0, and that's 0. So x plus y is in this set. And over here, P1 plus P2 is A1 plus A2 times x squared plus B1 plus B2 times x plus C1 plus C2. And that, again, is a quadratic in this form. The second property is, if I take any scalar alpha from F, then alpha times x is also in the set n of A. And to see this, you take A times alpha times x, and that can be rewritten as alpha times A times x, and that can be written as alpha times AX, which is alpha times 0, and that's just the 0 tuple. And over here, alpha times P1 is alpha A1 x squared plus alpha B1x plus alpha C1. Again, this is a quadratic in P2. So here, I have shown you two properties that are shared by both sets n of A and P2. So the first property is, if you take any two elements from the set, the sum of the two elements is still in the set. And if you take a scalar multiple of an element from the set, the result is also in the set. Now, these two properties are called closure properties. The first one is closure under addition, and the second is closure under scalar multiplication. There are actually many more properties satisfied by both sets. And if I let V be either n of A or P2, you can actually check that all these properties hold. And I'm going to show that this is the case for n of A. The details for checking that these are true for the case when V is P2 are left as an exercise. So here I take x, y, z from my set n of A. Now, the first property here clearly holds because tuple addition is associative, and this precisely is saying that addition is associative. Now, tuple addition also is commutative, so this also holds. What about the third property here? So we need to find an element called a zero vector such that if you add any other element from the set to it, you will still get back the element. And here I can just take the zero tuple. So I can write 0 sub n of A to be the n tuple of zeros. Now, what about the next one? Well, what we need is, for every element in n of A, I need another element so that if you add the 2, you get the zero vector. And in this case, it's very simple. For any element t in n of A, we just take the tuple whose entries are precisely the additive inverses of the entries in the tuple. So for example, if we're looking at F2, then the additive inverse of this would simply be this, the additive inverse of A in the first entry and the additive inverse of B in the second entry. So we have checked the first four properties. Now, these three properties obviously hold because F is a field, and scalar multiplication for tuples precisely satisfy these conditions. And the last one is also obvious, because if you take 1 times any tuple, you get back that tuple. So we have checked that n of a satisfy all these properties. And as I mentioned, you can also check that P2 also satisfy these properties. Now, there's no reason for me to restrict V just to n of a or P2. In fact, V can be any set I want as long as addition and scalar multiplication by scalars from F are defined over it. If V is closed under such operations and together with F satisfy all these properties, then what we have is called a vector space. And n of a as a special name is called the null space of the matrix A. So n of a is a vector space according to this definition. To end, I just want to mention a piece of notation. When you see x minus y, where x and y are from some vector space, then it actually means x plus the additive inverse of 1 times y. Finally, the elements of V are called vectors. Vector spaces are rather rich structures. There are many things that can be said about them. And we'll see some of the notions that come out of the study of vector spaces in future videos.